A few days ago, a telescope perched on a mountaintop in Chile released a single image that quietly contains more galaxies than every star visible to the naked eye from Earth on the clearest night of your entire life, combined many times over. Not stars, galaxies, whole island universes, each one containing hundreds of billions of their own stars, packed into one photograph so dense with information that scientists are still combing through it days later, still finding things nobody expected to see. This isn't a concept image or an artist's rendering. It's real light, captured by the largest digital camera ever built, pointed at a patch of sky astronomers have been staring at for over 2 decades. And what came back changed the resolution, the depth, and in some ways the entire working picture of that region of the universe almost overnight. The telescope is called the Vera C. Rubin Observatory. And if you haven't heard much about it yet, that's about to change. Because what it just did to a single famous, extremely well-studied patch of sky is only the opening act of what may be the most ambitious astronomical survey ever attempted in human history. Stay with me, because this story involves the woman whose work first proved that most of the universe is made of something we still can't see, a camera the size of a small car, and a single photograph that packs in more raw cosmic data than most entire research careers have ever produced. Let's start with what actually happened, because the details matter enormously here. On July 31st, 2026, the Vera C. Rubin Observatory released a new, extraordinarily deep image of a region of sky, known as the Cosmos Field, located in the constellation Sextans. If that name sounds familiar, it should, because the Cosmos Field isn't some random, obscure patch of empty space. Astronomers specifically selected it more than 2 decades ago, back in 2003, precisely because it faces away from the crowded, dusty plain of our own Milky Way galaxy, giving telescopes an unusually clear, relatively unobstructed window straight out into the deep universe. Since then, it has become one of the single most intensively studied patches of sky in the entire history of astronomy, repeatedly observed by the Hubble Space Telescope, the James Webb Space Telescope, the Chandra X-ray Observatory, and the Spitzer Space Telescope, among others. This is not new territory. This is, if anything, the most thoroughly mapped few square degrees of deep space that modern astronomy possesses. And that's exactly what makes Rubin's new image so remarkable. It managed to reveal something genuinely new inside a region that some of the most powerful telescopes ever built had already been staring at for over 20 years. Here's the number that should stop you in your tracks. Rubin's new Cosmos image contains more than 650,000 galaxies and over 50,000 stars, all captured in a single combined view. 650,000 galaxies, not stars within our own galaxy, entire other galaxies, each one potentially home to hundreds of billions of stars of its own, each one likely hosting its own planets, its own solar systems, its own unknown histories, stretching back across cosmic time. The image was built by stacking hundreds of individual observations together into what astronomers call a deep co-added image, essentially layering exposure on top of exposure to pull fainter and fainter light out of the darkness, revealing structures and objects too dim to show up in any single snapshot. The Cosmos Field itself is known to contain more than 2 million galaxies, stretching across roughly 75% of the entire age of the universe, some of them sitting as far as 12 billion light years away, meaning the light captured in Rubin's new image left some of those galaxies when the universe itself was still in its cosmic childhood, long before our own sun or solar system had even formed. Look closely at what's actually packed inside that single frame, and the variety on display becomes genuinely dizzying. Scientists cataloging the image have already identified spiral galaxies with delicate, sweeping arms of star formation, smooth, featureless elliptical galaxies built from older, more settled stellar populations, dramatically distorted galaxies, caught in the middle of violent mergers with their neighbors, gravity visibly tearing their structures apart and reshaping them in real time, and faint, reddish galaxies so distant that their light has been stretched and dimmed by the sheer expansion of space itself during its multi-billion-year journey to Earth. Only a relatively small handful of foreground stars, from our own Milky Way, appear scattered across the frame, which is actually part of what makes this particular field so scientifically valuable in the first place. With so little clutter from our own galactic neighborhood getting in the way, astronomers get an unusually clean, unobstructed view stretching deep into the background universe, layer after layer after layer of galaxies, receding away into the distant past. To understand how Rubin managed to pull this off in a region astronomers thought they already knew so well, you have to understand the machine responsible, because it genuinely is unlike anything that has ever pointed at the sky before. The observatory's centerpiece is something called the LSST Camera, mounted on the observatory's 8.4-meter Simon I survey telescope, and it holds the title of the largest digital camera ever constructed for astrophysics anywhere in the world. Its resolution is measured at 3.2 gigapixels, meaning a single exposure from this camera contains more than 3,200,000,000 individual pixels of information, a number so large that if you tried to display just one of its full-resolution images at normal viewing size, you would need a wall of ultra-high definition. Television's roughly 150 feet wide and 40 feet tall just to show the whole thing at once. This camera sits atop a mountain called Cerro Pachón, part of the Andes range in northern Chile, at an elevation of roughly 8,800 feet. A location chosen specifically because its combination of extremely dry air and exceptionally dark, stable night skies makes it one of the very best stargazing sites anywhere on the planet. The entire project is a roughly $800 million joint venture between the United States National Science Foundation and the Department of Energy, representing one of the largest coordinated scientific investments in ground-based astronomy in modern history. The camera's sheer physical construction is itself worth appreciating for a moment, because building a 3.2 gigapixel imaging system from scratch pushed engineering well, past what any prior astronomical camera had ever attempted, resulting in an instrument roughly the size of a small car, engineered with such precision that its focal plane sensors had to be cooled to extremely low temperatures just to minimize electronic noise while capturing extraordinarily faint light that has been traveling toward Earth for billions of years. But the camera and the mountain are really just the delivery mechanism for something even more ambitious, a 10-year survey program called the Legacy Survey of Space and Time, or LSST, which formally began science operations in June 2026. The core idea behind LSST is genuinely different from how most astronomical observation has traditionally worked. Historically, when astronomers wanted to study something specific, a particular galaxy, a particular star, a particular nebula, they would point a telescope directly at that one target, gather data, and move on to the next target. Rubin flips that entire approach on its head. Instead of hunting for individual targets, it's designed to repeatedly, systematically photograph the entire visible southern sky over and over again, every single clear night, for a full decade, essentially producing what astronomers have started calling an ultra-high definition, decade-long time-lapse movie of the universe. The comparison to a movie isn't just a loose metaphor either, because Rubin revisits the same patches of sky again and again throughout the survey. Astronomers can directly compare one night's observations against the next, automatically flagging anything that has brightened, dimmed, appeared, disappeared, or physically moved between visits, turning what used to be a static, one-time photograph of the sky into something closer to genuine, ongoing cosmic surveillance. Rubin is expected to capture millions of astronomical objects every single day, cataloging more than 100 objects every second it's actively observing, and generating up to 7 million automated alerts each night flagging anything that has changed, brightened, dimmed, moved, or exploded since the last time that same patch of sky was photographed. Over the full 10 years of the survey, astronomers project that T. Rubin will ultimately catalog somewhere in the neighborhood of 20 billion previously unseen galaxies and roughly 17 billion individual stars. Numbers so large, they're genuinely difficult to hold in your head in any meaningful way. The very first hints of what this machine was capable of arrived even before the survey officially began. During preliminary checkout observations conducted to calibrate and test the new system, Rubin had already detected more than 11,000 entirely new asteroids within our own solar system, including a meaningful number of near-Earth objects relevant to planetary defense, all captured essentially as a byproduct of engineers simply testing whether the telescope worked correctly. For context on just how extraordinary that number is, every other observatory on Earth and in space combined typically discovers around 20,000 new asteroids in an entire year of dedicated searching. Rubin matched more than half that annual global total during what amounted to its warm-up exercises. Once full, science operations properly began, that pace only accelerated. Within a relatively short window, Rubin had already sent out roughly 800,000 astronomical alerts flagging new asteroids, supernovae, and other short-lived, rapidly changing phenomena worth immediate follow-up attention from astronomers around the world. The observatory's very first public images, released back on June 23, 2025, gave the world its initial glimpse of what this level of sensitivity and scale actually looked like in practice. Those early images included a sweeping view of the Trifid Nebula and the Lagoon Nebula, along with a stunning wide-field look at the Virgo cluster, a massive collection of galaxies bound together by mutual gravity. That very first batch of released images alone contained approximately 10 million galaxies, along with 2,104 asteroids that had never been documented before, captured essentially as a test run for what the fully operational survey would eventually be capable of producing on an ongoing nightly basis. Astronomers who got early access to the first data described the experience in genuinely emotional terms. One researcher called the Virgo cluster images breathtaking, specifically praising how the level of detail managed to capture large-scale merging galaxies, the fine spiral structure of individual galaxies, more distant background galaxies, and foreground Milky Way stars all together within a single unified frame, something no previous single instrument had managed to pull off with quite this combination of breadth and precision. What makes the new Cosmos field released from July and August 2026 particularly significant within this larger story is that it marks something specific and important in Rubin's operational timeline. It represents the observatory's very first official science-grade image and data catalog release captured using the completed LSST camera system, an event scientists are calling Early Data Preview 2, or EDP2. This particular release combines science validation observations that Rubin collected between April 2025 and January 2026, meaning the spectacular image the public saw in early August wasn't captured in a single night, but rather represents months of accumulated observing time, carefully stacked and processed into one unified, extraordinarily deep view. According to Bob Blum, director of the Rubin Observatory at NSF's NOIR lab, this Cosmos image is genuinely just the opening move rather than the final word on what the observatory will ultimately reveal about this region, because of its enormous scientific value as one of astronomy's most thoroughly documented reference fields. Cosmos is specifically slated to be observed far more frequently than most other regions covered by the 10-year LSST survey, meaning Rubin will keep returning to this exact patch of sky again and again over the coming years, progressively building an even deeper, even more detailed picture, revealing fainter galaxies and finer structural details than even this genuinely spectacular first release managed to capture. A second phase of the same data release, expected sometime between October and December 2026, will add individual processed observation images and something astronomers call difference images, specialized processed frames that isolate and highlight only the things that have actually changed between one observation and the next, essentially building the raw material needed to start detecting supernovae, asteroids, and other transient cosmic events buried within this specific field going forward. To really appreciate why an observatory built primarily to survey billions of ordinary galaxies carries the name of one specific astronomer, you need to understand who Vera Rubin actually was and why her work fundamentally changed how humanity understands the universe. Vera Cooper Rubin was born in 1928 and spent the core of her career working closely alongside instrument maker and fellow astronomer Kent Ford, carefully measuring precisely how fast stars orbit around the centers of spiral galaxies. Beginning with detailed observations of the Andromeda Galaxy, our nearest large galactic neighbor, published in 1970, Rubin and Ford discovered something that directly contradicted what physics at the time confidently predicted. Based on simple Newtonian gravity and the visible distribution of stars within a galaxy, scientists expected that stars orbiting farther from a galaxy's center should move progressively slower, the exact same way planets farther from our sun orbit more slowly than planets closer in. Instead, Rubin found that stars in the outer regions of Andromeda were orbiting at essentially the same speed as stars much closer to the galactic center, producing what astronomers now call a flat rotation curve. Even more alarming from a physics standpoint, those outer stars were moving so fast that, based on the visible mass of stars and gas alone, they should have had nowhere near enough gravitational pull to hold together, and the entire galaxy should have flown apart into open space. As Rubin continued expanding her observations across more than 75 additional spiral galaxies throughout the 1970s, the exact same pattern kept reappearing over and over, refusing to go away as a fluke or a measurement error. The only explanation that could account for that much extra invisible gravitational pull was the presence of a massive, unseen reservoir of additional mass, matter that clearly exerted a gravitational influence but did not emit, absorb, or reflect light in any way that existing telescopes could detect. That invisible mass became known as dark matter, and while the theoretical possibility of some form of unseen missing mass had actually been proposed decades earlier by astronomer Fritz Zwicky in 1933, it was Rubin's meticulous, repeatedly confirmed observational data that transformed dark matter from a speculative curiosity into one of the central, foundational pillars of modern astrophysics and cosmology. It's worth noting that Rubin herself was notably cautious in how she framed her own results, often deliberately avoiding the term dark matter in her earliest published papers, and preferring instead to simply let the data speak plainly for itself, describing what she measured rather than speculating aggressively about what it ultimately meant. She also never sought sole credit for the discovery, consistently crediting her close collaborator Kent Ford, who built the sophisticated spectrograph instrument that made her precise velocity measurements possible in the first place. and emphasizing throughout her career that science functions best as a genuinely collective, collaborative endeavor rather than a showcase for any single individual's achievements. Other astronomers using entirely independent methods, including radio observations of neutral hydrogen gas at radio wavelengths, and later, large-scale gravitational lensing surveys, went on to confirm Rubin's flat rotation curve findings using completely different instruments and techniques. And by the early 1980s, dark matter had firmly moved from a speculative hypothesis into a genuinely central load-bearing pillar of modern astrophysics. Scientists now estimate that dark matter accounts for roughly 85% of all the matter in the entire universe, meaning the ordinary visible matter that makes up stars, planets, and every living thing, including you, represents only a small fraction of everything that actually exists. Despite the field-defining significance of her work, Rubin was famously never awarded a Nobel Prize before her death in 2016, an omission many within the astronomical community still consider one of the most glaring oversights in the prize's modern history. Throughout her career, she also remained a fierce, outspoken advocate for women in science, having personally faced considerable skepticism and institutional pushback as one of the few women working in observational astronomy during the middle of the 20th century, and she spent much of her later career deliberately opening doors, mentoring and encouraging the next generation of young women entering the field. It's genuinely fitting, then, that the observatory now bearing Rubin's name was purpose-built to hunt for exactly the kind of evidence that could finally reveal what dark matter and its equally mysterious cosmic counterpart dark energy actually are at a fundamental level. Rubin Observatory's decade-long survey isn't simply cataloging galaxies for the sake of having a bigger catalog. Its enormous, repeated wide-field observations are specifically designed to measure subtle gravitational lensing effects, the way massive foreground objects, including invisible dark matter, bend and distort the light of more distant background galaxies as it travels toward Earth, across an unprecedented number of galaxies and across the full 10-year timeline of the survey. By tracking how billions of galaxies are distributed and subtly distorted across the sky, and by watching how that distribution and the universe's overall rate of expansion evolve over the coming decade, cosmologists hope Rubin's data will finally offer serious new constraints on exactly how much dark matter and dark energy the universe actually contains, how they're distributed, and how they've shaped the large-scale structure of everything that exists. Questions that have remained stubbornly, frustratingly open ever since Rubin's own original rotation curve measurements first forced the scientific community to accept that the vast majority of the universe was, quite literally, invisible. So what does all of this actually mean for the 650,000 galaxies sitting inside the single new cosmos image? In the most immediate practical sense, it means astronomers now have an extraordinarily rich, freshly captured data set covering one of the best studied patches of sky in existence, ready to be cross-referenced against decades of prior observations from Hubble, Webb, Chandra, and Spitzer, allowing researchers to study everything from the detailed shapes of spiral galaxies with delicate, extended arms, to smooth, featureless elliptical galaxies, to dramatically distorted galaxies caught mid-collision as they merge together, to faint, extremely distant red galaxies representing some of the earliest, most ancient light in this particular field of view. It's also worth pausing on just how different Rubin's fundamental approach to astronomy is from virtually everything that came before it, because that difference is really the whole point of the project. Space telescopes like Hubble and Webb are extraordinary at doing one very specific thing exceptionally well: staring, with immense patience and precision, at a single tiny patch of sky for a very long time, pulling out extraordinarily fine, extraordinarily deep detail from that one narrow slice of the universe. Rubin was never designed to compete with that kind of pinpoint depth. It was designed to do something almost nobody had ever attempted at this scale before: survey essentially everything, repeatedly, systematically, continuously, trading some of that narrow, laser-focused depth for an almost unimaginable breadth and a genuinely new dimension entirely: time itself. A single Hubble or Webb image captures a frozen instant. Rubin, by returning to the same patches of sky over and over across a full decade, is instead building something closer to a genuine record of cosmic change, unfolding in something approaching real time, catching supernovae in the act of exploding, asteroids in the act of moving, and potentially entirely new, never-before-cataloged categories of transient cosmic phenomena that simply don't reveal themselves to a telescope that only ever looks once. But the deeper significance sits in what comes next, because this single image, spectacular as it already is, represents only the very first opening frame of a 10-year cosmic movie that has barely even started rolling. Rubin will return to the same patch of sky again and again throughout the coming decade, and each new visit adds another layer of depth, another chance to catch, something in the act of changing, exploding, or moving that a single static snapshot could never reveal. Somewhere within the 20 billion galaxies and 17 billion stars, this observatory is ultimately projected to catalog over its full survey lifetime almost certainly sit answers to some of the biggest remaining open questions in modern cosmology. Questions about the true nature of dark matter, the true nature of dark energy, and the ultimate fate of the universe itself. Questions that a single astronomer, staring patiently at a handful of spiral galaxies through a much smaller telescope more than 50 years ago, was the first person brave enough and careful enough to notice didn't quite add up.